So in 11.1, we did vectors in 2 dimensions, right? It was on a coordinate XY plane. Most of the math that you've done in general, calculus-wise anyway, has been 2 dimensions. The one exception that's on the top of my mind is when you do like solids of revolution, you start spinning things. That's definitely 3-dimensional. But this is 3-dimensional in a more concrete way than the spinning of the things around circles and around axes and stuff. We're going to look at vectors in space. So we're going to extend our ideas that we're in R2. This is the real number system, so this is 2 dimensions. That's what this means. So it's 2D. And we're going to expand them into 3 dimensions, 3D. And so being able to visualize 3D is not the easiest thing for everyone. I usually have to think about corners of rooms and things like that to get a good idea of what I've got going on. And my images, when I draw them, are not always the best, but I still try. Okay, so the first thing we're going to do is simply plot a point and what it would look like and think about how we would plot it in a kind of reasonable way to give some version of depth. Do any of you draw? Does anybody in here draw? Like, just raise your hand, tell me. Nobody. Y'all are like the second class that I've had where I've asked that question, and nobody says that they draw. Okay, well, we're just going to all do the best we can then. Okay, so our ordered triple, that's what this would be, is an ordered triple, is 3, 1, -5. So let me show you what we do in terms of our axes to draw 3 dimensions. We do a vertical axis like this, straight up and down, but this is the this is the axis, that we label Z. Okay, we label Z as the vertical axis. And then out the front, we draw kind of at an angle like this, the other two. The axis on the left is X, and the axis on the right is Y. Okay, pretty good so far. So this sort of has a 3-dimensional feel to it, looking at it, right? You have this picture that this X and this Y are sort of kind of coming out of the board at you. That's the feel it should have. So the first of the ordered triples is the value 3. So we're going to space out 3 on the x-axis. That's no problem. And then the next one is a y value of 1. But as I move out on the x-axis, like away from it, to a y value of 1, I need to do it parallel to the y-axis. So this dotted line is showing my movement, and I'm moving out parallel to the y-axis. Can you see that okay? So if I sort of boxed this in well, which it's not done well, but if you imagined, this would look like a rectangle. It's not great. Okay? So this is sort of where I am right now, but I'm in the plane xy, and now it says z is -5. So where do you suppose I'm going to go from here? I'm going to go down. Z is the up and the down. So from here, we're going to go down 5. And we're going to, I'll draw it out like this again too, literally count out 5 units. So I'm going to start here at 0. And then I've got 1, 2, 3, 4, and 5. And this is my ordered pair, or ordered triple, excuse me. If you want to give more of a dimensional effect to it, you can drop a few other dotted lines down. So you can drop it down like this and this. And you can piece it in so you can kind of see the rectangle that's being formed there. Okay, what do you think? I have an advantage because I've got the technology drawing some of it for me, right? But my disadvantage is the technology likes to also link things together, which is why I got a wonky looking rectangle at the beginning, is because it tried to hit my points and make them connect. So there's good and there's bad. All right, make it believable, make it look reasonable. We'll all be good with that, okay? Don't go in the wrong direction, clearly. I should probably identify for you that if you do have negative values, like a negative x or something like that, you are going backwards. So negative x is going over here, right? And negative y is going over here. And if we had gone in a positive z direction, we would have gone straight up like this, which would have felt a little funny because it looks like you're somehow still in the XY plane for a little while because it's 3-dimensional looking, right? The projection. So that's okay. All right, so we're going to do a lot of things here at the beginning. They're still not even vector things. They're just 3-dimensional things before we even get to the vector part of it. We'll go a little ways into this. Distance. how do you generally find distance when you're looking in the xy plane? Well, you subtract the x values and you square them. You subtract the y values and you square them. And you add it together and you take a square root. It's part of the Pythagorean theorem, along that idea. But we're going to do the same thing here, except that we're not just going to do it with x and y, we're also going to do it with z, right? It's just an extra layer at the end of what we're doing. So we're going to have a square root, and we're going to subtract x values first, in whichever order you like. I'm just going to go left to right, so 2 minus 5, and square it. Subtract y values, so I've got 1 minus 5, and then square it. Subtract z values, and I've got a 2 minus 2, and then I'm going to square it. Now, obviously, the 2 minus 2 is not adding anything to the discussion, right? But this is the form that we're going to do every time. We're going to find each of the values. So the first one is negative 3 squared, so that's 9. The second one is negative 4 squared, so that's 16. The last one's 0. 9 plus 16 is 25, and the square root of 25 is 5. So it's lovely. Okay, it's not always lovely, right? It's somebody's going to end up with square roots at the end. That's fine. But this is how you find distance in 3 dimensions, the same way you find it in 2 dimensions. No difference. Okay, so now let's consider having a 3-dimensional triangle. Okay, I'm about to look at we're not drawing this. I checked my paper just to make sure I didn't draw it. I was like, that would be awfully ambitious. We're not drawing it. Okay, but it says to consider the triangle with the following vertices. We're going to find the lengths of the sides and decide if it's a right triangle, an isosceles triangle, or neither. Okay, so right triangle would mean that it has to satisfy the Pythagorean theorem. Have a 90-degree angle and have to satisfy the Pythagorean theorem. What does isosceles mean? Remember? 2 sides that are the same length. We should be able to identify that quickly. It doesn't ask us if it's equilateral, but we could decide that too, right? We do know all 3 sides to be the same length. There's other things we could classify. So these are the classifications. So the first thing we have to do is to find the lengths of the sides, and it might be easiest if we give each of these ordered triples a letter name, right? So like calling this point A, point B, and point C, just for some notation to keep ourselves straight. So I need to find the lengths of 3 sides. How do I find the length of a side? Well, I use that distance formula done in the last problem with 2 points, and that's the length of that side. And then I do it with a different 2 points, and then I do it with a different 2 points, and there's only 3 sides that are going to come about with 3 points. So we'll start with AB. Okay, so notationally, you may remember, I have the advantage because I'm doing geometry again every night, 3 times, because my children are geometry. Notation to think about. When you write the segment AB like that with no segment on top, it means length. When you put the segment on top, it means segment. You've got the rays on top or the lines on top and so forth. This means length. So we're actually going to take the square root and we're going to subtract the x values, y values, and z values. So if you'll notice, the x values for A and B actually match, correct? So we have -1 minus -1. That one's actually going to be 0. The y values, is 0 minus 5, so that one's going to be 5. And then the z values are -2 minus 2, so that one's 4. Whoa. Squared, that's 4. So the first one is 0. The second one is 4 squared. And then, 5 squared, and the last one is 4 squared. Okay, so 5 squared is 25. 4 squared is 16. 25 and 16 is what? 41. That doesn't simplify, right? So square root of 41. So that's AB. I'm going to take that and shrink it so that we have a little bit more space for the next one. Oops, not like that. One more time. Okay, let's just do BC. So BC, I have the first one, or the x value, so -1 minus -3 squared plus, I have 5 minus -1 squared, and I have 2 minus 1 squared. All right, so -1 minus -3 would be 2 squared. So I have 2 squared here. In the middle, I have 5 minus -1, so this is 6. So I have 6 squared. And at the end, 2 minus 1 would be 1 squared. So I have 4 plus 36. That should be a plus, sorry, plus 1. So what does this give me? Square root of 41. Now, this tells us that we have at least an isosceles triangle, right? Because we do have two sides that are equal. Now, you can have a triangle that's both isosceles and right. So be careful. This isn't a multiple choice where it's this answer, or none of the above, right? It could be one where it says both A and B are correct kind of thing. Y'all have taken those multiple choice tests before, right? Okay, so we have a third side as well, and we need that third side in order to establish whether it's a right triangle at this point. So we need to do side AC. So we have, let's see, I'll go still from A to C. So I have -1 minus -3 plus 0 minus -1 and -2 minus 1. Is it minus negative? No, minus 1. Okay. So -1 minus -3 is 2. So this is 2 squared, right? I have a 1 squared in the middle. And let's see, we have -2 minus 1. We have a 3 squared at the end. Does that look okay? Remember, I'm ignoring signs because I'm squaring things. That's the only reason that's happening. But so 2 squared is 4, plus 1 would be 5. 5 plus 9 would be 14. Okay. All right. So I claim that this is not a right triangle, and I don't have to do very much work to prove it. How can I know so quickly? I didn't do any calculations.
You've got 2 equivalent sides, and that other side is smaller than both of them.
Got it. Very good, Jackson. If you have a right triangle, the hypotenuse is the biggest angle, or biggest side, excuse me, because it's opposite the biggest angle. Well, the non-equal side, which is my square root of 14, is smaller. Oh, I think I missed something when I moved that over. I'm sorry, square root of 41. It's smaller than the two sides that are equal. So it can't be a hypotenuse, right? So it didn't ask us to justify whether it is or it isn't. If it did, and it didn't specify exactly how, we could language argue that, correct? Right? We could do that. This is an isosceles triangle, and it is not a right triangle. I think that's a good place to stop for today.